YouTube. Okay, so we had a quick question about why we're doing this. Good question. So basically we talked yesterday about how the bus is a series of wires. In this example, we're using 4 because 4 is a friendly number. But it's got a bunch of zeros and ones, which is true and false, right?
Yeah.
So it goes to the location, right? So it comes from your chip. It goes to your other thing, because my brain stopped, based
Okay.
off of the zeros and ones, and that's where your instructions live.
Master controller.
There you go, the master controller. It goes into your controller based off of which wires the stuff goes down, basically. That's how it was explained to me. 0101. Yeah. Sends a little signal, and that's where the instruction lives. So that's all we're doing is we're imitating we're pretending that we're a computer.
Okay.
So in order to do that, it'll be these operations. That is the way I understood it to be. And I remember asking way back in the day when I was a stage manager, I actually asked a question about binary to my director, who was a retired nuclear submariner. And he worked on their computer systems, and he gave me like really
Oh,
mean.
okay. I was trying to figure out why you were asking him about binary. Okay.
Well, because at the time I was actually going back and forth between studying music and studying computer science. Um, and I could not wrap my mind around binary. And I asked him what it was and what it was for and why. And he said because of the way that things go down wires, and all of these are off and this one is on. So it just
Yeah,
kind of
just
sends the beeps and boops.
just like a light switch. I mean, you turn the light switch on and your lights come on, turn it off, lights go off.
And the little
Waking up that particular place, right?
Yep. So this is the series of signals, and the computer interprets it to go to these locations, and the beep boops happen.
Beep boops. I
Yep.
like that.
So that is why we're doing that. So we didn't code this because it's really long and annoying, and we would have been here forever.
Oh, that's all the run function?
Oh yeah,
Wow.
here's the run function, operation, and PC. So
Lots of elves. Or
yeah,
elves, as June likes to call them.
it's a lot of elf statements. Um, so there is an easier one that we'll do at the end of the week. And oh, y'all are smart. You can tell that these are numbers, so we're not gonna.
So basically, you're going through and using each one of the methods that we defined above, right?
Mhm. So
Okay.
we're checking if the operation that we're going to use is one of these operations, and then we're going to do a function based off of what we just sent to it. That's pretty much it.
Okay, but you're using a counter. So why are we using a counter there? The PC plus.
We because we are we're shifting things over. That's all.
Oh, okay. So it's just moving along, kind of like a pointer would on a linked list to find something.
Yep, our PC was our pointer. I think we talked about that yesterday up at the top.
Okay, you said the PC was a pointer and then you changed and said the SP was.
Yes, they're both pointers. It's the best way to
Oh,
do it. There's
oh,
because the self.pc only lives at 0, 1, and 2, and this lives at another location.
okay.
We don't really move this pointer. It just exists. Um,
Now
thus far, anyway. Oops.
scroll all the way back down.
Self.
Oh, I didn't even see that.
It's self-referential.
Scroll all the way back down, hun.
See, little.
Okay. Yeah, did we do that one? I don't
No,
remember.
that's today.
Oh, okay.
And this is that was also yesterday. We just moved the PC. That's part of the little like run operator that we didn't do last night. We are going to talk about Bitwise operations today.
The XOR. Okay.
And apparently there's also so there is single and I suddenly can't draw the and. How does the and look? It's this way. Okay. It's the man dragging his butt across the floor.
You almost had it. It's the where you go up and
There we
around,
go.
back down. There you go.
Oh, see, to me that
Well, that looks like a treble clef.
that was a treble clef. I'm trying to remember how to draw it because I draw my ands this way.
Yeah, I do when I'm writing something out.
There you go. Is the man scooting his booty? Or
Hey,
is that
here.
it? Or does it still look like a treble clef?
It looks like a treble clef.
Oh man, guys.
You're going backwards the other way around. And
Okay.
the loop de loop goes around the other side, doesn't it?
I honest to Zeus, I don't know.
Hey, you're getting closer.
Okay, you might have been a musician if.
You can't draw the ampersand, but you can draw a bunch of treble clefs.
Is that there we go. There's the ampersand. Looks like a dude scooting his booty across the floor. Okay, we've got single and single or a and or um exclusive or
Are you gonna turn your camera on tonight or no?
I don't know.
You're gonna be a duck tonight.
Quack.
Hey, Carmen.
Carmen, what's up? Um this tilde, which is the tilde, which was neither. Someone sending me a message. What's up? Chat is orange.
Yeah, she's just saying that she can't talk, but she's here.
Okay, there was a tilde. The NOT gate, also called the inverter. Okay, single. Okay, and or.
Yeah, the tilde, that's like an approximation, right?
Normally, but if you watched the Bitwise Operations pre-work video, he
I did.
was using. Nobody ever does.
I watched the ones in data science.
Oh, everybody's expecting me to like watch the video, all the videos, and then be able to like distill computer science into a quick study session.
Mm-hmm.
It's so much sometimes. I try. Okay. There's a tilde, this, da, 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 da. Okay. So basically, we're talking about true-false math, which is great for me because guess what true-false math doesn't actually technically involve as long as you rewrite all the problems.
Well, it still involves zeros and ones.
Yep, but one is a true and the other one is a false. And when I had to do binary math before, you bet that I went through and changed everything to T's and F's. Because that way they don't start moving around on me. Again, hello YouTube. I have dyscalculia, which is basically dyslexia but numbers. And Lord have mercy, strings of zeros and ones and zeros literally just are the worst. That was the worst. All kinds of fun. So, I change everything to T's and F's because my T's and F's stay in the exact same spot. But essentially, it's just some logic. So, the quick and dirty version is that with an and, they both must be true. So if you have a true and true, true plus true equals
True.
true. False and false equals,
Well, false, right? Or is that still true? That's still true for an and.
false and false is false. They must both be equivalent, basically. If true and false, O and 1 is O. Okay?
Carmen says false.
Yes. True and false is false. So basically, this is, we can call this politics math if we want to be really snarky about it. It's politics math. So,
what is that table called? I can't remember now if it was in CS or if it was in data science that I learned about it. But there's like a table to where you have two values that are either true or false. I think that was in the CS50. That might have
yes.
been where it was at. Okay.
It's also down here, and I'm just not showing it.
Oh, okay.
I think it's on here. It's in the video. No, it's in the video. Okay. Let me see if I can quickly find it in the video. Alrighty. There's your and your ors. Nice little table here. Of course, red doesn't stand out against that, so we'll just fold that up a bit. This doesn't work on screen share. Yes, it does. All right. So 0 and 0. So if both A and B are false, that's false. If A is false and B is true, it's false. If A is true and B is false, it's false. And if A is true and B is true, it's true.
Yeah.
Then we have the or operation, which is one or the other. If
so true precedence on the or.
Mm-hmm.
Okay.
If one or the other is true, then it's true. So if true and false, false. If true and true, true. If false and false, false. If false and true, true.
No, that one would be false, wouldn't it?
False, false. Yep, sorry. Lord have mercy. Brain. False and true, false. I was just testing you.
Yep.
So now we're going to, now going back, let me just change my little, my and symbol over here to an or. which is a straight line, or, which is not complicated for anybody, if true or false is true.
That's true.
True or false is true. False or false is true.
False.
True or false.
True.
Very good. So that's pretty straightforward. We've been doing that for a while with our loops, but we've been using ands and ors. We've been using a double. Now we're doing a singular.
Wait a minute. We weren't doing doubles on the ands, and ors, were we?
I
think that's, well, I know in C you got to do double ands and double ors.
Yeah, this lecture was in C, and also we do have double ands in JavaScript.
Oh, okay. Yeah, because Python you don't do doubles.
Yes. I don't know why this video was in C, to be completely honest. That definitely kind of threw me for a bit of a loop.
Maybe they stole it from CS50.
Lambda back in the day used to teach back in the day Lambda used to teach C.
Oh, okay.
So this might just be a really old video. So now we have we have XOR, NOR, and NAND. So this is exclusive, neither nor, or I don't really know how to do NAND. I can't come up with a word. So NAND. Nah. Okay, so basically these are inverted. So let's start with NAND. So let's do another true, false, false. Now this is where we get into what I was calling the political math. False, true, and true, true. Now if we start with NAND, so NAND, it's basically the opposite of everything we've done before. So true, false, normally would be false.
So then it would be true?
Yep. False and false is now true. False and true is true. True and true is false. So it's basically just the inversion of the and that we had before, right? Where we had false, 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 true.
Yeah.
That's all it is the political math. Now we have true and false. So previously this would have been.
So if it's, what is in or, that mean?
Neither, this is the opposite of.
Okay, the opposite of.
So previously, true and false would have, like, if either this or this is true, then this is true. But if this or this is false, so if neither this nor this is true, so
okay.
False.
So it's basically like and or is similar to and.
Yeah, in or is basically the opposite of a normal or, is the basic, but the easiest way to put it.
Okay.
So a normal or would say this is true, and an or says this is false. So false.
So false and false is normally false, then false and false would be true this time.
Yeah. Yeah, that's basically how this works. It's a little mind-bending. So all it is basically is the opposite. And then we have again, true, no, this is false, true. So whatever it would have been is the opposite. So in this case, or the N basically creates an opposite of effect. If we look up at the video that no one watched. So here we go, our NAND, see? is all the opposite. So A and B, before we had 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. The opposite is 0 and 0 is 1, 0 and 1 is 1, 1 and 0 is 1, 1 and 1 is 0. So we see how it is the opposite, right?
Yep.
All right, which is super cool. We all love that. And now we have the same thing with NOR. So 0 and 0, still 0. 0 or 1 is 1. So this is the OR table. 1 or 0 is 1, and 1 is 1. So we have these ones, right? So basically now we're just paying attention to, so it's just inverted. So observe.
So 1 is representative of true and 0 is representative of false.
Yes.
Okay.
Because otherwise, world goes batty. So if we can see here, all we've done is inverted it. Everybody good?
You transposed it.
Yeah. We've transposed it to opposite land.
Now, XOR.
XOR is cool. This is exclusive OR.
Mm-hmm.
So this is either one or the other is true. Exclusive OR is only. Okay. So exclusive
I was catching on to that. That was
so exclusive OR. So one or the other, right? So we got two falses. It's false. A true exclusive OR. So one or the other. Then it's true. If one or the other, that's the X, is true, they're both true, it's false.
Explain to me why, if they're both true, it's false. Because that part's what's throwing me off.
It is exclusive. So you only want one thing to be true.
Oh, okay, never mind.
Like, for example, as we're making our political jokes, you can't vote twice. You can't vote for A and also vote for B. If you have voted for A and B, you're a bad person. Your vote is thrown out, ergo false, and you spend time and then you go to jail.
do not collect $200. Do not pass go.
Well, you got
Right.
to catch me first.
Dang, Doc. Oh my god.
You can only attend one university at a time, in theory, unless you're a genius and probably also 12. So, you can't go to Harvard. And, you can't be in two places at once.
There
I'm
you
going
go.
to Harvard and Lambda.
Let me introduce you to cyberspace.
All we need is a time turner to do this.
Okay, you know what? Bye. Done. I'm done.
She said she's done.
Right? You can only make a decision. You make one or the other. That's essentially the thing. You can't choose both.
Okay, cool.
I like XOR.
Yeah.
I like XOR too.
And
You can't marry two people, so one or the other.
All right. So does this one make sense?
Yep.
All right, cool. That's it. That's the end of computer science. Bye, guys.
That's not the end of computer science.
Actually, this is the end of the topic tonight. The project has nothing to do with this little topic for reasons unknown.
Oh, okay.
So
it's only been 30 minutes. This class is too short.
Yeah. Let's go back to other things.
What did you talk about yesterday?
We talked about
decimals, binary, and hexadecimals.
Okay.
We talked about how to convert manually into binary and manually into hexadecimal.
Okay.
And we also talked about the innards of a computer.
So
Okay.
Yeah, lots of buses.
so quick. Well, this is not going to be quick.
Ava's growing an affinity for numbers.
No, she's not. But Ava understands other people need help too.
Well, I will have the recording up from last night tonight.
Okay.
I was working
That's amazing.
and was rewatching the edited version just to make sure I didn't miss anything.
Wow.
All right. Well, I'll go back and watch that because I've been watching tutorials all day. And I just started trying to teach myself NumPy because I really could not figure out the whole array and string manipulation stuff. So I figured maybe I could use NumPy to try to pass the GCA. But anyways, we'll see. We'll see how it goes.
NumPy is very useful. NumPy and pandas.
Yeah.
Yeah, even if it doesn't help you pass the GCA, knowing NumPy is not a bad thing.
Yeah.
So you kind of came in when we were talking about true and false for our numbers.
Mm-hmm.
So right now, we can consider that all of these values are false. 0, 0, 0, 0, 0, 0, 0 has no value.
Okay.
Everything is false. Right?
Mm-hmm.
So each one of these zeros is a placeholder for a different number, which I've very helpfully written up above. 1, 2, 4, 8, 16, 32, 64, 128. And when you turn each of these zeros to a 1, it gives that a value that placeholder has now a value of true, basically. So 7 zeros and a 1 now has the value of 1 because the 1's place is true. If we did the same thing and we turned the 8's place on, the 8 plus 1, the 8's value is true, the 1's value is true. So it's 9.
It's kind of like in our math to where you've got the ones place, you got the tens place, you got the hundreds place. Well, instead of having in multiples of 10, you're going by the power of 2.
I see.
And if this gives you a headache, you are not alone. But if you think about it as true and false, and these being their placeholders, right? So this is the values up here. So if for some odd reason we wanted to put up 135, we can start with 128 is true because that's less than 135, right? So you have 135 less 128 is some number I'm not going to deal with, but I know I need a 2.
It's 7.
7? All right, well, I got a 2, so now it's 130. And I've got 5 left over, so I can do a 4 and a 1.
And then you would add the zeros in between the ones.
Yep. So all of these, so now we have our value of 135 down here with our 128 true, false, true, true, true.
And that's what it would really look like in binary?
Yes.
So to make one, what was the number 135 in binary? It's 100001111.
Yes.
That's pretty cool.
If you look up above, it's like the numbers that are the 4, 2, and 1. And then the 128 down on the end. So if you add those up, you get, if you add 128 to 4 to 2 to 1, then you end up with 135.
That's pretty cool.
So that is...
I actually like that.
Yep.
So we're just using these as our true placeholders, that the 4, 2, and 1 are true. 128 is true, so these are the numbers that we count, and the 0 gets passed down. because we're not counting down, because we're not counting our zeros when we add them together. Another 0 because I missed it.
Okay.
That's it.
That's pretty cool.
That is the quick and dirty version of that. And hexadecimal is the same. We have relatively the same. We have 4 digits on either side. So we have an 8-digit number.
Mm-hmm.
But this time, we're representing numbers 0 through 9. And if it's higher than 9, it goes A to F.
And this is how we make colors, right?
Yeah.
Among
Kind
other things.
Yes, among other things.
Among other things. Okay.
So this is the part that kind of throws. It doesn't seem self-explanatory. None of this seems self-explanatory. But it goes 1, 2, 4, 8.
Those
And
are powers of 2.
Then again,
So
it goes
2 to
1,
the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, which is 16.
and 1, 2,
Etc.
4, 8 again. So this isn't 100. Like last time, this was 128. 100 and yeah, it was 128 over here.
Yep.
This time it's 8. So if we had our number, so let's just take our wonderful number 1011 and 1001. So 1001 is 8 plus 1,
9.
right? So that's
9.
9.
Mm-hmm.
My pointy drawy thing keeps turning off, and it's making me sad. So this side is 9.
Mm-hmm.
And this side, 1011, is
11.
So this side is 11. Now we can't. Now hex doesn't have 11. This number doesn't exist. But A starts at 10. So if A is 10, then what number is 11?
B.
Right. So this number here, 10111001, is represented in hexadecimal as B9.
Okay.
Bingo!
That makes sense.
Awesome.
Yep. And the other relationship is, so the decimal system, which is the one we're most familiar with, is based on tens, right?
Mm-hmm.
So that's 0 through 9. And binary is base 2. So that's 0 through 1. And hex is base 16. So that's 0 through 15. Right? So does that make sense?
Well, I'm not understanding the 0 through 15.
Okay, so if you count in hex, you start at 0 through 9, and then you add A through F, right? And F equals 15.
Okay.
So in binary, so binary is 2. So you end up with 2 minus 1. Decimal is based on tens, so you end up with 10 minus 1. And base 16.
Okay.
And it's -1 because we start at
0.
0.
Yay, everyone's favorite number.